We want to find the reaction at pin C. So it's a pin, it's going to have an X component and a Y component. I'll call it CX and CY. We can't just draw the external picture because we'll have four unknowns in that picture, AX, AY, CX, CY. So because it's statically indeterminate and it's made up of multiple members, I'm going to go right to drawing what the individual members look like or what's happening to those individual members. The order I do it in does not matter, but sometimes drawing all my pictures and then looking at them, equation-wise, I might have a better idea of, if I'm solving this by hand, where should I start? I'm going to draw my first picture. I'm going to draw the beam that goes from B to C. I'm separating it from the pin at C. I'm also separating it from its pin connection at point B. I'm just looking at the beam itself. I have two external forces acting on it. Which I'll copy down. I have that support at point C, which I modeled just like I have been. I can say it has an X component, I'll call CX, and a Y component, I'll call CY. What's new here is at B, it's pinned to another member. It's not pinned to an external support, but it's still a pin connection. It still behaves the same way. But we'll see how it is a little bit different when we get to the second diagram. So that pin at B is also going to have an X component and a Y component in it. I'm going to assume BX is pointing to the right and BY is up. And this assumption is arbitrary right now, but it does impact the later steps, as we'll see in 1 second when we look at the second free body diagram. But my beam BC, this is its complete free body diagram here. But we see we have four unknowns still by drawing this diagram, so this alone will not be enough information to solve for both CX and CY, which is ultimately what we're trying to find. But because we have multiple members, I can draw more free body diagrams. I'm actually going to hold off writing equations from this just because I have too many unknowns. So my hope is sometimes one of my free body diagrams will have only three unknowns attached to it, and that's a good place to start then. For my second picture, I'm going to draw what's happening to AB. No external forces acting on it. There's that support at A, which is a pin. It will have those two components, AX, AY. And now the crucial step at B that very commonly is not done correctly. B is an internal connection, I'll call it. It's connecting two of my members together. So it's still a pin, but it's different than A, it's different than C. What I have to pay attention to is I assumed in my first picture BX was right, BY was up. Crucial step here, whatever I assumed here, I must make the opposite assumption here. What I'm actually drawing when I'm drawing these, BX, BY, this is what member 2 does to member 1. In this picture, because of Newton's law, every action has an equal and opposite reaction. This BX and BY, that is what member 1 does to member 2. So because they're acting in opposite directions, that's why whatever assumption I make here, I have to draw it in the opposite direction in the other picture. That's when two members are pinned together. When there's three or more members pinned together, it's more complicated than this. But most commonly, this is the type of thing we're going to see. So again, it doesn't, if in this picture I said it was left and down, that would have been okay. But then in this picture, it would have had to been up and right. If I look at these two, before we get to the equation step, I have CX, CY, BX, and BY. In picture 2, I have AX, AY, but again I have BX, BY. Between my two pictures, I only have 6 unique unknowns. And because each one's a rigid body, I can get 3 equations out of each. So I will be able to develop 6 equations for my 6 unknowns between these 2 pictures. This has 4 unknowns in it, and 2 has 4 unknowns in it. Again, if one of my pictures had only 3 unknowns, I would start there. Because they both have 4, it doesn't really matter where I start writing my equations. So I'll just start with picture 1. And actually, I will start by summing the moments in picture 1. The moment, like before, it doesn't actually matter where you sum the moments about. You'll still be able to get the right equations, but solving it by hand, you can make your life a little bit easier for yourself if you take this rule of thumb into account. On any free body diagram where summing moments, it's usually better to sum the moments about a point that only occurs in a single diagram. So here, because B is in diagram 1 and B is in diagram 2, I'm going to usually be better off if I sum it not around B, which means since B is a pin, C is a pin, that means C is the best choice in picture 1 to sum my moments around. The reason this is helpful is because when we start developing these simultaneous equations, if I can get equations that just have bx, by, and then another set of equations that just have bx, by hand, that's going to be easier to solve. If I took the sum of moments around B here and around B here, I don't have those linking equations as readily available. They'll still all be correct, but it's going to be harder to solve. By summing moments around C, I'll get 500 times 3, positive, plus 400 times 6. And the way I drew it in picture 1, minus 9by. So just integrating the solve step here, I can actually find by from this first equation. By, I get 433 pounds. Ultimately, I don't care what by is, at least for what we were asked to find, but I do need to find it in order to get to finding cy and cx. I have different options here. I could actually take the moments, I could also take the moments around B and solve for cy. I generally, though, recommend only do 1 moment equation per free body diagram, just so for more consistency, because it's possible that if you do the moments wrong, you could get non-unique equations. So I will proceed as before by now summing forces in 2 directions. So in the y direction, I'll have by minus 400 minus 500 plus cy. And now actually here, since I know by, I can find cy. One of my unknowns I now have. Cy is 467 pounds, and it is up. I assumed it was up, and the positive means I was right. And finally, I still need Cx. I can start to get it by summing forces in the x direction, but this is where we now need that second picture to make any more progress. Bx I don't know, Cx I don't know. I know they're equal and opposite, but I only have this equation left to use and still 2 unknowns. Now we can go to that second free body diagram and get 3 more equations. If I sum forces in the x, just to start somewhere in my second diagram, I'll get that ax minus bx is equal to 0. So ax is equal to bx. If I sum in the y direction, I'll get that ay minus by is 0. So ay and by are equal to each other. And if I take a moment, this is where, again, that rule of thumb is going to be helpful to us. It's usually best to take a moment about a point that only appears in one free body diagram. In this case, since B appears in free body diagram 1 and free body diagram 2, I would recommend taking about A. They're both pins, but A only appears in one picture, so the equation it gives us will be often more useful to us when we're solving this by hand. When I solve for the moments around A, I'll get 4bx minus 3by is equal to 0. If I now look at the 6 equations I have 6 unknowns, and like I just said, I have 6 equations. So I will be able to know that this is a solvable system that I've created. Again, by at this point, I already know its values. So I can solve for ay right now. Using equation 5, I know that ay is going to be 433 pounds. And that will be up. Now, since I know the value of by from equation 1, I can use equation 6 to solve for bx. Bx is the only unknown in this equation, so bx, I'm going to get a value, 325 pounds. Knowing bx, I can get, really what I'm mostly interested for this problem is the value of cx. So now going to equation 3, solving for cx, I get cx is negative 325 pounds. I assume that it was to the right. It's actually to the left. So as far as the final answers go, that's what I was looking for, the vertical and horizontal components of the pin C. But by just starting with that first free body diagram, I had no way of knowing what Cx was. I had to go to that second free body diagram to get enough equations to be able to solve the rest of this. So an alternate way to do this, knowing it's a two-force member, I can actually solve it with just a single free body diagram. I can solve it by just drawing BC. And we'll see why in a second. I have those same applied forces. I still have that Cx and Cy. What changes, knowing that AB is a two-force member, is that B, I don't have to write it as Bx and By, because that's saying I don't know its magnitude and I don't know its direction. So it introduces those two unknowns at B. But knowing it's a two-force member, I know the direction of that force has to be going from A to B. So what that tells me is I know the orientation here. I can say this is acting at a 3, 4, 5 triangle. And I can just call this simply force B. Again, effectively, if I look at this, now in my picture, there's only 3 unknowns. There's Cx, Cy, and B. Whereas if I didn't use the information as a two-force member, I have both Bx and By because I did not know its direction. So I have only 3 unknowns in this new picture, and I can get 3 equations out of it. I will be able to solve just from one free body diagram for the values of Cx and Cy. I won't go through all the steps, but if we take sum of forces in the x, I'll have sum of b, and I'll have Cx in it. If I take the moment around C, I can immediately get b. And then if I take the sum of forces in the y, I can get the value of Cy once I know the value of b.